environmental engineering. The title of the module is Water Quality, Quantity, and Pipe Network. Now, we are going to discuss a topic, water resources, specifically focusing on surface and subsurface sources of the water. Water is the most fundamental resource for human survival, and as a civil engineers, you will play a crucial role in planning, designing, and managing water supply systems. Let us begin. First, look at the definition in the slide. Surface water resources are those sources of water in which the water flows over the surface of the earth and is directly available for water supply. Let me simplify this. Any water that you can see flowing or stored on the earth surface is called surface water. The examples include rivers, lakes, ponds, as well as the reservoirs. Now, think about this. When rain falls, where does the water go? Some water infiltrates into the ground, which becomes a groundwater. Some flows over the land, that is referred to as the runoff. This runoff, it will be eventually collects in streams, rivers, as well as the lakes. And this becomes the surface water resources. Now, let us move to the first type of surface source, that is the ponds and the lakes. It is a natural large size depression formed within the surface of the earth. When it gets filled with water, it is known as the pond or the lake. Now, what is meant by depression? It is a low-lying area in land. When rainwater accumulates in such area, it forms a pond. If it is small in size, we are referring to as the ponds. Now, similar to that, if it is larger in size, we are referring the same as the lake. The major difference between the pond and the lake in terms of depth is the pond will be usually shallow, whereas the lakes will be, it is greater in the depth. Whereas in terms of usage, you look into that, the pond usage is limited and the lake may serve as the major water supply to the cities. So the simple way to remember is, if it is small depression, we are referring to as the pond. If it is a larger depression, we are referring to as the lake. Now, the water quality in ponds and the lakes, we are going to discuss as the next point. The quality of water is generally good and does not need much purification because water stays for a longer time, suspended particles will settle down, and natural purification also will happen. In real lives, the lakes may contain algae, organic matter, or bacteria. So the treatment is required before using the water for different activities. When you look in terms of the quantity of water, if the quantity is generally small, that is the ponds, it cannot serve the large city. It is used mainly for rural and small communities. In villages, ponds are used for washing, irrigation, and sometimes it will be used for consumption also after basic treatment. In cities, lakes like Chembrabakam Lake are used for water supply also. Now let us move to the second type, that is the streams and the river. Small stream channels feed their water to lakes or rivers. The streams are smaller water courses, whereas the rivers are larger and more significant. Larger and perennial streams may be used as water sources also. Now we will look into that. What is meant by perennial? This is a very important term. Perennial means the water will flows throughout the year. You can take example as the Ganga river. Whereas the non-perennial means the flow will occur only during the rainy season. Now the rivers as the water sources. The rivers are the most important source of water for public water supply systems. Why we are preferring the rivers? Because it is a continuous supply, larger quantity, and it can serve the cities also. In addition, the rivers may be perennial, that is water available throughout the year that we have discussed already, which is the reliable source of water. Next, the quantity of water is more. Compared to ponds and the lakes, rivers have the larger flowing water and it will also have the larger catchment area. When we look into the quality of water is not reliable, okay, why the river water is not reliable in terms of quality? Because the industrial discharge, sewage entry, as well as due to the agricultural runoff. So the quality of water keeps changing on this. You can take the example, during monsoon season, the water becomes muddy. During summer, the pollutants become more concentrated. So the water must be properly analyzed and treated. Before supplying water, we should analyze it in means of testing, and we should purify the water also in means of the treatment. Let us first understand what a storage reservoir is. It is a barrier in the form of a dam which is constructed across a river. Now what happens when we build a dam? The water that flows downstream gets obstructed and starts accumulating on the upstream side. This accumulated water forms what we call a storage reservoir, essentially an artificial lake created behind a dam. Now, why do we create storage reservoirs? What is its purpose? First, covering the irrigation needs. These reservoirs stores large volumes of water which can be released in a controlled manner for irrigation. This is extremely important in agriculture, especially in regions where rainfall is seasonal. Second, quantity and quality improvement. When the water is stored, we can regulate supply during dry periods. Also, some amount of natural settling happens in reservoirs. We can slightly improve water quality by allowing suspended particles to settle. For example, in Tamil Nadu, reservoirs like Mettur Dam plays a vital role in supporting agriculture in the Kaveri Delta region. So, whenever you see a dam, remember it is not just blocking water, it is storing, regulating, and managing water resources efficiently. Now let us move to the next important topic, subsurface water sources, specifically groundwater. Groundwater can be defined as the portion of precipitation, that is rainfall, that percolates downward through the soil and enters the pores and cracks in soil and rock formations. Some of this water remains stored underground, while some may eventually emerge back to the surface through the sprinkler wells. Imagine rain falling on the ground. Now, all water flows away as runoff. Some of it slowly seep into the ground. This process is referred to as the infiltration. As it moves deeper, it fills the empty space between the soil particles and the rocky layers. This stored water is referred to as the groundwater. Now we will look into the importance of the groundwater. Groundwater is extremely important. In fact, it is the most important source of water supply for rural communities across the world. In many villages, people depend entirely on the wells, borewells, or hand pumps for their daily needs. Now, let us discuss the advantages of groundwater one by one. It is free from disease causing microorganisms. Groundwater is comparatively safer than surface water because as water percolates through soil layers, natural filtration occurs. Soils acts like a filter and removes many harmful microorganisms. So, groundwater is generally less contaminated. Next, it can be used without extensive treatment. If groundwater is properly protected and extracted, it can often be used with a minimal treatment, unlike surface water which requires extensive purification. This makes it a cost-effective option, especially in the rural areas. And the third one is the no evaporation loss. This is a very important point. The surface water bodies like lakes and the reservoirs lose water due to evaporation, especially in the hot climates. But groundwater is stored underground, so evaporation losses are almost negligible. And next is it is economical and practical. The groundwater systems like wells and boreholes are often simpler and cheaper to construct and maintain compared to larger dams or treatment plants. So, from an engineering and economic perspective, groundwater is a very practical solution. And the final thing is the local availability. Groundwater is usually available near the place of use itself. For example, near a village. This reduces the need for long pipelines and transportation infrastructure. Now we will look into the disadvantages of the groundwater. However, like any sources, groundwater also has its own limitation. It requires pumping. Unlike surface water that flows naturally, groundwater usually needs to be pumped. This requires energy, either electricity or manual effort, especially in the deep borewells. It also have high dissolved minerals. Groundwater often contains dissolved minerals such as calcium, magnesium, iron, or even harmful substances like fluoride. This can lead to issues like hard water or health problems if it is not treated properly. Also, it is poor in oxygen content. Groundwater generally has low dissolved oxygen compared to the surface water. This makes it less suitable for certain biological process and can affect the taste as well as the quality. Now let us move to a very important topic, water demand. Whenever we design any water supply system, whether for a village, town or city, the first and the most important question we must answer is how much water is actually required. That requirement is what we call as the water demand. Now, components of the water demand we will discuss now. Now, the total water demand of a community is not just for drinking. It includes several components. Let us go through each one in a detailed way. The first is the domestic water demand. This is the most basic and the essential component. It includes water used for daily household activities such as drinking, cooking, washing clothes, as well as cleaning the utensils. For example, in urban areas, domestic demand is usually higher because of lifestyle and higher living standards. The next one is the industrial water demand. Industries require water for manufacturing process, cooling of machinery, as well as cleaning and the maintenance. For example, industries like textile, paper, and steel require huge quantities of the water. So, in an industrial city, this component can dominate the total demand. The next one is the institutional and commercial demand. This includes water used in schools, colleges, hospitals, offices, hotels, as well as in the shopping complexes. These places serve large number of people, so their water requirement is significant. Next one is the demand for public uses. This is often overlooked, but this is a very important component. It includes water used for public parks and gardens, street washing, public fountains, and sanitation. These uses improves the public hygiene and environmental quality. Next one is the fire demand. Now, this is the critical safety requirement. In case of fire accidents, a large quantity of water is needed instantly. So, for designing a water supply system, engineers must ensure that sufficient water is available for firefighting purposes. The next one is the losses and the wastage. This is very practical and important point. Not all supplied water reaches the consumer. Some amount is lost due to leakage in pipes, illegal connections, theft, as well as due to the poor maintenance. This is called unaccounted for water or losses. So we must include additional water to compensate for these losses. Now, next we will discuss about the factors affecting the water demand. Now that we understand the components, let us see what factors influences the water demand. The first one is the climate. In hot climates, people consume more water for drinking, bathing, and cooking. Whereas in colder regions, water demand is comparatively lower. So, temperature and weather conditions directly affect the water usage. Next one is the geographic location. The location of a place also plays a crucial role. For example, coastal areas may have different usage patterns. Hilly regions may have limited access to the water. So, the geography influences both availability and the demand. Next one is the size, population, and the economic condition. This is one of the most important factors. As population increases, water demand increases proportionally. Next one is the standard of living. In higher income communities, water usage is higher due to more appliances, better sanitation, and lifestyle habits also. So, demand is not just about number of people, but also how they live. Next one is the extent of the industrialization. If an area has more industries, water demand will increase significantly. For example, a city with many factories will require more water than a purely residential town. Next component is metering, cost, and supply pressure. This is very interesting engineering aspect. The metered supply. When the water is metered, people tend to use it more carefully. Next one is the cost of water. If water is expensive, the consumption decreases. The next one is the supply pressure. If the pressure is high, more water may be wasted through leaks or excessive use. So these factors influences the consumer behavior and system efficiency. As engineers, we must understand that water demand is not fixed. It is dynamic and varies with time, location, and socio-economic condition. That's why proper estimation of water demand is very critical in designing a sustainable water supply systems. We are going to discuss a topic, domestic water demand. Let us first understand what domestic water demand means. Domestic water demand refers to the quantity of water required for household activities. These activities include everyday uses such as drinking, cooking, bathing, washing clothes and utensils, flushing toilets, gardening and lawn sprinkling, general cleaning and sanitation. So essentially, this is the water required to maintain a basic standard of living in residential areas. We have standard values, that is IS code references. For metropolitan or larger cities, the recommended domestic water consumption is 200 liters per head per day. For small towns and cities, it is 135 liters per head per day. Per head per day means that amount of water required by one person in one day. So, if a city has a population of 1 lakh people and each person needs 200 liters, then the total demand becomes very large. This is how engineers estimate the water supply requirements. Now we will look into the breakdown of the domestic water consumption. Now let us look at how this total water is actually used in different activities. For drinking, in metropolitan cities, it is 5 liters, and in small city also it is 5 liters. This is interesting. Drinking water requirement is almost same everywhere because human physiological needs do not change much. Next one is that cooking. For cooking, in both metropolitans and small cities, it is 5 liters. Again, you can observe that the cooking requirement remains fairly constant. And for bathing in metropolitan cities, it is 75 liters, whereas in small cities, it is 55 liters. Here, you can see a significant difference because people in metropolitan city tends to use the showers, whereas in smaller towns, water is relatively conservative. Next, we will look into the washing of the clothes. In metropolitan cities, it is 25 liters, whereas in small city, it is 20 liters. This difference is mainly due to washing machines in cities and more frequent washing. Next, we will look into the washing of the utensils. In metropolitan cities, it is 15 liters, and in small cities, it is 10 liters. Again, lifestyle and water availability influences the usage here. When you look into the washing and cleaning of houses, in metropolitan cities, it is 15 liters, and whereas in small city, it is 10 liters. That urban households often use more water for floor cleaning, maintenance of larger living spaces. Next is the lawn watering and gardening. In metropolitan cities, it is 15 liters, whereas in small city, it is negligible. This is because metropolitan houses may have lawns or gardens. Small towns may not have a structured landscaping. When you look into the flushing of the water closets, in metropolitan cities, it is 45 liters, whereas in the small city, it is 30 liters. This is one of the major components of the domestic water demand because the modern flush system in cities consume more water compared to the traditional systems. So finally, when we add all these components, total domestic water demand in metropolitan cities, it is 200 liters per person per day, whereas in small city, it is 135 liters per person per day. This matches the highest standard values which we have discussed earlier. In this slide, we are going to discuss an important component of urban water supply planning, that is non-domestic water demand. Specifically, here we will focus 4 categories. First one is that industrial water demand. Next one is that institutional and commercial water demand, followed by public water demand and fire demand. These components are very important because in real world planning, what is not only used for domestic purposes, a city must supply water to industries, public services, and also maintain readiness for emergencies like fire. Let us begin with an industrial water demand. Industrial water demand refers to the amount of water required for industries within a city, whether they are already existing or planned for future development. Now, industries use water for multiple purposes. The first one is that manufacturing processes, cooling systems, cleaning and washing, boiler feed water, and transportation of the materials. So, depending on the type of industry, the water requirement can vary significantly. For example, a textile industry uses much more water compared to a small assembly unit. However, for planning purposes, instead of calculating each industry individually, we use a standard estimate. Typically, the per capita industrial water demand is taken as 50 liters per head per day. This value helps engineers include industrial water demand in the total water supply calculation of a city. Next, let us move to institutional and commercial water demand. This category includes water required for hospitals, hotels, restaurants, schools and colleges, railway station, offices, small scale industries. Now, these facilities are essential for the functioning of a city. Even though they are not heavy industries, they collectively consume a considerable amount of water. For example, hospitals need water for sanitation, patient care, and cleaning. Hotels and restaurants require water for cooking, cleaning, and guest use. Educational institutions need water for drinking, toilets, and laboratories. So again, instead of calculating each separately, we use an average estimate. The average per capita demand for this category is 20 liters per person per day. This value is added to the total demand when designing water supply systems. Now let us discuss the public water demand. This is the water required for maintaining public amenities and services in a city. These examples include watering public parks and gardens, road washing and street cleaning, operation of public fountains, maintenance of public buildings, sprinkling water on roads to control the dust. Even though this demand may seem small individually, it becomes significant when considered for an entire city. The average per capita public demand is taken as 10 liters per person per day. This ensures that public infrastructure remains clean, green, and functional. Finally, we come to a very critical component, that is the fire demand. Fire demand refers to the quantity of water required for firefighting purposes. Now, unlike other demand, this is not a regular daily consumption. Instead, it is an emergency requirement. However, it is extremely important because fires can occur unexpectedly. Large volumes of water are required in a short time. Public safety depends on adequate fire water availability. One important point to understand is that fire demand is not based on per capita consumption alone, but is usually calculated as a function of the population. There are several empirical formulas used to estimate the fire demand. Some commonly used one includes Quichling's formula, Freeman's formula, NBF formula, and final is the Buston's formula. Each of these formulas relates fire demand to population size and helps engineers estimate the required capacity for fire protection systems. In this segment, we are going to discuss how to estimate fire demand using empirical formulas. In the previous slide, we understood that fire demand is an emergency requirement, and unlike domestic or industrial demand, it is not continuous. However, it is very critical for safety, and therefore it must be properly estimated while designing a water supply system. To estimate fire demand, engineers use empirical formulas, which are based mainly on the population of the city. Now we will discuss these formulas. The Quichling's formulas, let us begin with the Quichling's formulas. It is Q is equal to 3182 square root of the P. Q represents the quantity of water required for firefighting expressed in liters per minute, whereas the P represents the population in thousands. Now let us understand this conceptually. This formula shows that fire demand increases with population, but not linearly. It increases with the square root of a population. What does this mean? If population increases 4 times, fire demand increases only about 2 times. So the increase is gradual, but it is not proportional. This reflects real life conditions where larger cities need more fire protection, but not in direct proportion to the population. Next is the Freeman's formula. It is Q is equal to 1136 P divided by 10 plus the 10, whereas Q is the liters per minute, whereas P is in the population in thousands. Now observe this formula carefully. It has two components, a term proportion to population, that is P divided by 10, and next you are having that constant term, that is 10. This means even for smaller towns, a minimum fire demand is ensured. So compared to Quichling's formula, Freeman's formula gives a slightly higher and more conservative estimate. Accounts for base level fire protection requirement also. Next, we will move into the National Board of Fire Underwriters formula. Now we will discuss this formula in detail. This formula is specifically applicable for central congested cities. These are cities where buildings are closely packed, property value is high, and fire risk is more severe. Look at the first case one. Here, that is the population is less than or equal to 2 lakh. Okay, so for that formula is Q is equal to 4637 square root of P 1 minus 0.01 square root of the P, where Q is the fire demand in liters per minute, where P is the population in thousands. Now, this formula is slightly more complex. It includes a square root term, which is similar to the Queteling formula. We have also have a correction factor, that is 1 minus 0.01 square root of the P. This correction factor reduces the rate of increase as population grows, making the estimate more realistic. Now, let us come to the second case. For us, whereas for cities with population greater than 2 lakh, a base provision of 54,600 liters per minute is made over here. Additionally, an extra provision ranging from 9,100 to 36,400 liters per minute is added for the fire demand. This reflects the fact that larger cities require high capacity firefighting systems and fire risk is significantly higher due to the dense infrastructure. In continuation to the previous slide, small or low buildings, small houses or low-rise buildings typically require about 2,200 liters per minute. These include individual houses or sparsely populated areas where consumption is relatively moderate. When we move to larger buildings such as multi-story apartments, the demand increases to around 4,500 liters per minute because more people are concentrated in a smaller area and facilities like lift, common water usage and higher occupancy also increases the demand. In high value residential and apartments, demand rises further between 7,650 to 13,500 liters per minute. This is because of higher lifestyle standards, increased water usage, as well as greater per capita consumption. In highly dense areas with 3-story buildings, demand can go up to 27,000 liters per minute. This reflects the impact of population density. More people directly mean higher water demand. Now, instead of memorizing the fixed values, engineers often use empirical formulas to estimate the water demand. One such widely used relation is the Burston's formula. Here, Q is equal to 5663 square root of the P. Let me explain this clearly. Q represents the quantity of water required and it is measured in liters per minute, where P represents the population, but note carefully, it is expressed in 1000. This formula shows that water demand is proportional to the square root of the population, not directly proportional. This is very important. Why we are having the square root? Because as population increases, some facilities are shared over there and efficiency improves. As not everyone uses peak demand simultaneously. So demand increases, but not in a linear scale. Now, even after estimating the demand, the actual water supply must be higher than the calculated demand because of losses and wastage in the system. What are the causes of the water loss? The leakage. Water may be lost due to pipe leakages, old or damaged pipelines, poor plumbing systems, sometimes meter issues. The meters are faulty or meters are tampered or even stolen in some cases. This leads to the inaccurate measurement and losses. So, it is estimated that about 15% of the total water consumption can be lost due to these factors. This is significant. So, when designing systems, engineers must add extra capacity to compensate for this loss. What are the factors affecting the losses? Let us understand what influences these losses. Watertight joints. If joints are not properly sealed, leakage increases. Pressure in the distribution system. Higher pressure can lead to the higher leakage. So pressure management is critical. Next one is the system of the supply. Continuous supply system tends to have fewer contamination issues but may increase leakage if it is not maintained properly. Metering, if you're telling proper metering means it ensures the accountability, reduced wastage and better monitoring. And unauthorized connections. Illegal connections are a major issue, especially in the urban areas, which leads to the water theft, pressure drop and inefficient distribution. We are going to discuss a topic, per capita demand. This concept is fundamental because it helps us estimate how much water is required for a population, which is essential for designing water supply systems. Let us begin with the definition. Per capita demand is defined as the annual average quantity of water required per person per day. Now, this is very important. It is not just domestic water usage. It includes several components. First is the domestic use, which comprises of drinking, cooking, bathing, and washing. Industrial and commercial use comprises of the water used in small industries, shops, and the offices. And for public use, it includes parks, street cleaning, and firefighting also. And wastage and thefts includes leakage, illegal connections, and the system loss. So, per capita demand is actually a comprehensive measure of total water requirement per person. Now, let us look at how we express this mathematically. Mathematically, per capita demand is equal to total yearly water requirement of the city in liters divided by 365 into design population. Let me explain each term clearly. That is Q, per capita demand. This is the water required per person per day, usually expressed in liters per capita per day, where V is the total yearly water requirement. This is the total quantity of water required for the entire city in 1 year, which has been measured in liters. Whereas the P, it is the design population. This is the population for which the system is designed. Now we are having 365. This represents the number of days in a year, converting annual demand into a daily demand. So we have discussed now about the water sources, that is the surface water sources as well as the subsurface water sources, and the various types of demand as well as the per capita demand. The rest of the things we will discuss in the next video. Thank you.